So hi everyone, my name is James Willis. I'm from SciNet at the University of Toronto, where I'm an analyst, where I help with user tickets, I help with porting code, scaling code to thousands of cores, and I also help out with teaching as well. And today I'm going to go through numerical libraries. So I'm going to start by explaining a bit about modular programming. Eric touched upon it on Tuesday's course, and then I'm going to go through how you would implement it with a couple of examples. And then I'll use that to lead into libraries and how we build them and how we install them on clusters. I'll touch briefly on module systems on HPC clusters, and then in the second half I'm going to go on to specific scientific libraries with a couple of examples using the GNU Scientific Library and with CUDA FFT in Python. So if there's one takeaway that I want you to take from this talk is please don't reinvent the wheel. If you want to implement some code, like if it's a very generic algorithm, there's probably already a library out there that has been heavily optimized by a dedicated team and has been tested extensively. So please use that. So prevents headaches and you going through coding that you don't really need to do. Okay, so scientific software can be a very large and complicated beast with a lot of subtleties, and typically the complexity grows as the number of lines squared. As it gets larger and larger, it gets much more complicated. I think the number of lines in GROMACS was like 2.5 million lines of code, so very complicated. And when you're implementing things, you're either recoding the same thing that's already been done or you're copy and pasting from elsewhere. And this can lead to a lot of mistakes or potential mistakes. So this is sort of the motivation behind modular programming. So how do we actually do modular programming? So first you want to, instead of just diving in straight into the implementation of the code, we want you to take a step back first and look from a top-level perspective and design the code in such a way that you separate out the header files, so the interfaces, what we call the API, the Application Programming Interface, into header files in C++ and interfaces in Fortran's case. And then you want to have the source files in a separate file. And what this does is it enforces boundaries between files, and it makes it much easier to prevent bugs in the future. Another thing, just please avoid global variables. They are the worst. Try and encapsulate your variables inside of classes, again, to avoid headaches further down the line. And what this helps with is modules are much easier to unit test because you have encapsulated one type of functionality in one module. And what we can do is we can unit test modules individually, and then from that build up to what are called integration tests. So then you test modules together and test that interface. Another advantage is with modular programming, when you come to rebuild the software, it's much more efficient. It's easier for tools like Make and CMake to compile a code when it's in a modular form. And also when you come to modify code, it's much easier. Okay, I want to edit this function that implements, that calls an FFT library, for example, and I know it's in that part of the code, in that module. We can more easily find it and edit it. And what also becomes more powerful is version control. So this is Git and GitHub. In terms of when you add new lines of code, you're only editing one file versus multiple files. So when you come to, in the future, if you find a bug, for example, you know exactly where to look in the Git commit history. Okay, so how do we actually do this in practice? A modular program requires like several object files to be compiled and then linked together at the next stage. So I'll just go through a quick example. So say you have a main program called app, and it contains library calls to, let's say we just call it a library, which is .cpp in C++ and F90 in Fortran. And what we'll do is we'll access the functions from the API in the header files. That's where we'll get the top level view of the libraries. And then from there, we'll compile, can you see my, yes. So we'll compile the main program first, and then each library file to an object file. And then at the linker stage, which is this here, we'll link the object files together to create our executable. And this is very similar between C++ and Fortran here. Just for this example, I just wrote out the compiler lines, but in practice, please use some auto build tools such as make and CMake to compile your code, because it'll make your life much easier. So we've compiled one library with functionality, and we've used it in one application. But what if we want to use the same library in another application without having to recompile the library again? How do we achieve that? So what we'll do is we'll take our header files, our interface files in Fortran's case, and object files, and we'll copy them to separate directories in a common location. So this is just an example, just a base directory. We'll put the header files, so the interface files, in the include directory, and the object files in the library directories. And once we've done that, we have to let the compiler know where these libraries exist when we come to compile. And we'll use the -i flag to specify the include directories. And just for now, we'll include the absolute path for the object files when we come to link. So again, we come to the compile line here. We specify I to show where the header files are. We'll compile our application that calls the library functions, remember, and then that gets compiled into an object file, and then to compile to link to the binary to create that, we'll specify the path to the library file, the object file there. Again, it's similar in Fortran's case. Now, so that was just a toy example of how we create a basic library and compile it in a program. With real libraries that are very similar to this. Again, they have to be, most of the time they have to be built and installed in a common location with distinction between header files for the interface and library files for the actual source code, the object files. In Linux, for example, a lot of the libraries start with a lib prefix and end in either .a or .so. So these two extensions, I'm not going to go into detail here, but they just stand for the .a files are static libraries, and .so files are the shared object files. So more for dynamically linked libraries. So what we'll do is we'll compile our application, again specify the full path to our library, just in like the previous example. But instead of giving the explicit path in the linker command, because you don't want to have to specify the full path every single time you link against the library, what we can do is we can use the -L flag. And what this does, you could specifies the location of where all the libraries exist. And then we use the lowercase l to just give the name of the library So just shown in this case here. And we don't need to add the lib prefix of the library name. We just use -lowercase l here. And what this means, we can just specify one common location for all libraries and then specify the name of every single library we link against after the object file here. Yeah, we have to make sure that we specify the library files after the object files that link against them, just because of the order of how the compiler links the files together. Are there any questions so far before I continue? Okay, so I've just got a few more notes on libraries here. We have the standard C++ libraries such as Vector and CMath. You don't have to specify I and the L flags because these are already sort of inbuilt into the compiler. The compiler knows intrinsically where to find them. So you don't have to specify in this case. And I'm going to list a couple of cases where I and L are not actually needed. So this is when libraries have been installed in what's called a standard directory on the system. So this is, for example, /user include and /user lib. So when this occurs, you don't need to specify capital I and L. You just have to specify the name of the library. If you're on a HPC cluster and you're using the module systems, when you load the module, the environment is set up such that you don't need to specify I and L. So it's very handy to use modules on HPC clusters. And if you're working on a HPC cluster, you can't use a package manager because you can't install things as your user. But if you're working on your laptop, if you're using apt like on Ubuntu, they'll install it in a standard location. So again, you don't need to specify the path to the libraries. But yes, the name of the library is still needed when you link against it because it needs to know which library you want to link against. Now, if you are compiling your own libraries in non-standard locations, so if you're compiling it from source, you'll still need to specify I and L and the lowercase l for the name of it. Because the compiler, we just need to let the compiler know where to look for the libraries. So I just wanted to show this as an example. So if you attended the MPI course on Monday and Tuesday, the MPI CC command, all it's doing is it's wrapping the GCC command with a bunch of includes and locations of libraries to link against. And then here we can see it's linking against the MPI library and the Fortran version of that. And the same goes for the Fortran compiler as well. So this is all going on behind the scenes when you call an MPI CC. So software modules are a common way to set up a shared system of libraries on supercomputer clusters, so all of the users can access them. How it works is you can install the same library with multiple versions. It's a very powerful tool. And if you want to see what modules are available, you can use the module avail command. It'll show all the available modules. And if you want to access a specific module, you can use, so for example, if you want to load the OpenBlast library, you can try module avail OpenBlast and module help. The command I use most of the time is this module spider, and this will give you a list of dependencies of modules to load before OpenBlast in order to load. Because sometimes if you just do module load OpenBlast, it'll say can't find the module or you need to load a series of modules beforehand. Module spider helps you in giving you this dependency tree. Yeah, and before compiling and running, you need to load the module because it doesn't know where to find the module in the first place with the libraries. So this is a common occurrence. So if your package manager doesn't have the library that you need, or the software is not installed in the module system on the HPC cluster, and you don't have permission to install the package in the system paths, what do? What you can do is you can compile it from source and specify the base directory of the path to where you want to install it. So the common installation procedure, if you're downloading a package from GitHub or GitLab, for example, they'll use either the auto tools or CMake. And the first step is you want to specify the prefix. So this is the location where you want to install the library. And once you've done that, then you just run make. So you compile the code and make install. All make install does is it copies the object files and the header files of the library to this prefix base directory that you've specified in this first step. It's very similar to CMake. CMake just has a different flag to specify the prefix directory. But you have to make sure that the base directory is a directory that you have write permissions, because it'll compile, but then when you come to make install, you'll get a bunch of errors saying no write access to this directory. So typically you'll put it in your home directory when you're installing the library. So if you want to use libraries in a non-standard location, again, specify I and L flags to your compilation commands, just to let the compiler know where to link against, where to find the library to link against. Now, if you're lazy like me and you don't want to specify these flags every single time you compile, you can use these set of environment variables. Now, what these do is the add, you can modify, so I'll just go through each one of them. So this is in the Linux environment variables. So cpath is where the compiler will look for header files, for interface files. So we just modify that and add the include path to this new library that you want to compile against. The same goes for the library files themselves, the object files. If you modify the library path and just give it the base directory and /lib to alert the compiler of where to look for them. When it comes to running your library, sometimes the library will be, or your executable will be dynamically linked. So it only links in the libraries at runtime. You need to specify the LD library path. So that's just the same as the library path, but it'll look at runtime. This is where it looks for the libraries. So you can either run these commands in the terminal before you come to compile, or you can just, what I do is I just add them to my .bashrc. So every time I log into the system, it automatically adds these paths to my environment. Yes, and the LD library path, yeah, is for at the runtime step. If your library also includes binary applications, so commands, you'll also need to set the path of your environment. So what this means, so it'll look in the binary location, the binary directory. So if you start typing a command from any path, any location, it should autocomplete because Linux will look in that location when it comes to running the command. Okay, so that comes to about roughly halfway. So in the second part of the talk, I wanted to go through the series of scientific libraries that are out there that you can utilize. So I'm going to start by going through some CPU ones. So we have BLAS, which is for basic linear algebra operations. Then we have LAPAC, which is for linear solvers and eigenvalue problems. And then we have a a distributed version of LAPACK called SkillLAPACK. These are mostly in C, C++, and Fortran, but we have some Python interfaces also. These are, I'm not as familiar with these ones, but these can be used for eigenvalue problems. And then Boost is a common one. It's a C++ source library. That should be, it's very well peer-reviewed, a portable library. Then we have eigen, which can be used for matrices and vectors, vector operations. And then this is quite a common one, is FFTW, which is the fastest Fourier transform in the West. This is I think the de facto fastest FFT library to use. Then we have our file format libraries, such as HDF5 and NetCDF. These are portable across architectures, and it just sets your output files in a common format, so then multiple file readers can read them. And then we have the GNU scientific library, which is a numerical analysis library. I'm going to go through in a couple of slides an example of how to use this. And then we have PETSC, which is a scalable parallel solution for partial differential equations. And then we have a series of other libraries, which we have Armadillo, Blaze, dlib, and a machine learning algorithm. So those were the CPU ones. And then we have a list of GPU equivalent. So we have BLAS again, but now it's QBLAS. So this is a CUDA compiled library for NVIDIA GPUs. And we have, again, the equivalent for AMD GPUs, which is RockBLAS. Then we have QSolver and RockSolver. And sparse, these would be for, sparse matrix operations. And this CUDA FFT is implementation on an NVIDIA GPU for fast Fourier transforms. But as you can see, there's like equivalents in both different architectures, just to make sure it's optimized for that specific instruction set. So now I'll move on to the Python libraries. If you attended Ramses's HPC Python program on Wednesday, he went through the NumPy library, which is for faster arrays in Python. Then we have SciPy, which is a lot of scientific analysis tools are in that library. Then we have Number, which is a just-in-time compilation of a series of Python and NumPy code to run fast machine code. Then Pandas, I think, was introduced yesterday at the Big Data talk. This is just for accessing tabular data and manipulation. Then we have scikit-learn for machine learning algorithms. And then, of course, TensorFlow and PyTorch, which are used for neural nets and deep learning. Okay, so now I want to go through an example of using the GNU scientific library in C++. So GSL has been implemented as a C library, and it has a series of useful tools for root finding, for minimization, sorting. There's a lot of calculus libraries, functionality in there with statistics and histograms and fitting. You can also use it for Monte Carlo integration, ordinary differential equations, polynomials, and of course matrix and vector operations. So as we're dealing with a C library, we'll probably have to look at dealing with pointers and casting when we come to our example. So imagine we want to find the root for where this equation is equal to 0. So this just has a series of trigonometric functions and some quadratic terms in our function here. If we want to use GSL, we first have to set up our code such that the code knows what interface to use in GSL. So we look at the roots header file. Then we want to create a structure that specifies each of the coefficients of our function, and then define how we evaluate the function in the first place. So all we're doing here is we're sort of translating the problem in a way that GSL can understand it and compute the solution. And then what we'll do is we'll set a guess on the lower and upper limits of where we think the root is for x, and just give it a series of coefficient values. So we'll create our solver here with a pointer, and then we'll allocate a bit of memory for the function. And then we'll create a wrapper for the function just to point to the example function we've created here. And we'll pass it the list of arguments that we've set in the structure parameters here. And then we'll pass all of that to our root solver in GSL. Now how this will work is we'll iterate around how you calculate the root, and you'll call the GSL function multiple times until we get the right solution or it's close enough given an error. So we'll call iterate, and that will return a value if you call these other series of functions given the upper and lower bound. It will refine them until it finds the right solution. So we'll just print out each iteration what the upper and lower, the new guess is, and what the root it thinks it is. And then we'll also look at testing the interval. So we'll check whether the value is close enough to what we think the root should be, and we'll give it a error bound. So as long as it's close enough, within 1,000th of the value, we'll ask it to stop. So at the end, we'll check what the status of this function is. So it'll either be continue, we haven't refined and iterated enough to get the solution, or we'll continue. And then also if we can't find the root in 100 iterations, we'll exit out as well, because it could go on forever. And then finally, we will free the memory we've allocated at the start of the function. So that was a lot of stuff in GSL, but essentially what we're doing is we're just wrapping up the problem so that GSL can understand and interpret what we want it to calculate. There are some pointers and typecasts, but that's because we're dealing with a C library. So how do we compile this on the command line? So this is on Bridges 2. We'll first load the C compiler, or the C++ compiler. We'll compile our source code, and remember we need to link in the libraries that we're using by giving the names here after the compiled source code. Remember, when you're using software modules, you don't need to specify capital I and capital L flags. Normally, GSL is a module, but on Bridges 2, it's automatically in the environment, so we don't need to load that on Bridges. And this is the given output. So we can see that we give it the initial guess on the upper and lower bound of what we think x is. It'll return the root, and it'll give you the error on that root that it's calculated. That is not within the error bound that we've specified, so we'll go on to the next iteration and the next iteration until finally we have a root which is close enough so that the error is small enough that we have found our root for that particular function. If you want to find out more about, well, specifically root finding, there's a good GSL documentation on this site here. But that's essentially it for that example. I'm going to move on. Are there any questions so far before I move on? Okay. So now I'm going to go through a Python example. So what if you only like running in Python? That's not a problem. Most numerical libraries will have a Python interface that you can call directly. But what if you come into a library that doesn't have a Python interface? What you can do is you can create your own wrapper using PyBind, ctypes, Swig, or f2py in Fortran's case. And you just essentially wrap the function that you're trying to call with PyBind, and you can call it directly from a Python script. So I'm going to go through a quick example using PyBind 11. So as an example, suppose we want to call the CUDA FFT library, which you can use to calculate a Fourier transform, but do it in Python. What we first want to do is write a function in C++ that wraps the library call, and then use PyBind to create sort of a Python package, and then you import that in your Python script to call it. Yeah, so note that there's a lot of GPU-based FFT libraries out there with a Python interface. This is just an example of how you would use PyBind. So again, what we do is we include the header files from CUDA FFT, and we're writing this in C++, so it looks very complicated, but all we're doing is we're calling CUDA malloc. So on a GPU, you have to allocate the memory on the GPU first from the CPU, and then copy our input data to the GPU, and then make sure that we have an array to copy the result to on the CPU. That's all we're doing here with the CUDA malloc, allocating some memory on the GPU. And then we need to set up what's called a plan, but this is the kernel that we want to execute on the GPU. And then actually execute the plan on the GPU itself. And then when we have computed our result, we copy the result back to the CPU from the GPU, and make sure that so that's what this memcopy device to host is here. And we make sure that we free the memory on the GPU and destroy the kernel that we created to compute the calculation. So that's the C++ side of things. Now when we use PyBind, again, we'll include the headers to the PyBind library. And all we do is we create a module, and we just give it a name. So we're going to call this PyCUDA FFT, and just give it a description of what it is. So all we're doing is we're wrapping the CUDA FFT library, remember? And we are defining a function in this Python package called FFT. And then we just want to point it to the FFT function that we've created there. Okay, so then how do we actually use this in Python? So this is just a simple Python script. We want to import a Python package. So that's the one we've created with PyBind called PyCUDA FFT. We'll import NumPy, and then we'll just give it a series of input variables to compute on the GPU. So we just have the angular, the angular resolution here, the size of the FFT, and we give them the times, and we specify the x values with sinusoid. And then all we do is we reference the Python package that we've created, and we call the function given the input array. And then we'll just take the magnitude of our result and print it to the terminal. Well, that's essentially it. I think, yeah, so the return type on the wrap function is a list, but we can ask PyBind to return a full NumPy array, but that doesn't fit on one slide, so I did it differently here. So if you want, you can try to run this example on Bridges. So if you log on to Bridges first, and copy Ramses's Python environment from his directory called HPC PyCode, then we can activate the environment and load the CUDA module and compile our shared object file. So all we're using here is the NVIDIA C compiler. We are compiling with a C++ 17 standard. We're compiling the shared object file, and we want to have an optimized binary here. And then this is the PyBind parts here, where we call PyBind to wrap the C++ library call in our function here. And this is our the PyCUDA FFT file here. That's why it has a .cu file extension. And what that'll do is it'll create a shared object file here, and we just specify the object file name. And again, remember to link against the CUDA FFT library by specifying the name at the end here. And then you can try running the script. So this should run the script on Bridges 2 and should return the result. So I don't know if you want to, we have, I guess, 9 minutes left. I wasn't sure how much time I would have. If you want to try and do that, I can come and help you if you have problems. But I'll summarize here before we run out of time is, again, the biggest takeaways I want to get across is please don't reinvent the wheel. Reuse these mature libraries that have been extensively tested, optimized. If you think you can implement a fast library, you can't. These have dedicated teams in order to do that, and have been working on it a long time. Yeah, this is key as well. Use mature libraries from a well-known source. So if you've been collaborating in a field, if the sense is it's a good library and it's been well tested, please use those first before using smaller, less well-known libraries. Yeah, they've been developed, maintained, debugged, tested, and optimized to the nth degree, and they're really good at the task in question that you want to achieve. Yeah, and libraries are the cornerstone of both academia and industry, and they've been heavily used in a professional software development setting. So if you're thinking about maybe going into industry, they are well used there as well. So that you can learn while you're doing your PhD to help you get a step up when you move to industry. And again, I'm sort of reiterating Eric's point on Tuesday. Try and include further software engineering elements in your day-to-day work, because it'll save you headaches in the future when you come to debug code, or if you want to reference specific versions of your application in papers, so you can have other people reproduce your work. Try and use automation tools such as Make and CMake to build your code. Eric also mentioned the thing called continuous integration. So this is when GitHub will run tests every time you commit to the repository, so that you can know if there's an error or a bug in any particular commit to the repository, rather than you coming, I don't know, months, years down the line, finding this bug and not knowing where it is. Repositories and GitHub will help you with that. And that is all I had time with. I left 5 minutes for questions. So if anybody has further questions or is trying to run the example, yes?
I was trying.
Have you loaded?
Yeah, I got the code downloaded.
Code is GCC loaded also? Oh, okay. I tested this recently. I thought it worked. I can come and help. Yeah, that's the problem with PDFs and copying commands. I think next time I'll.
Should we remove this one?
Sorry?
Should we remove this part?
If you can fit it all in one line, that's all those slashes are doing. Oh, in that example, there was no space in between MVCC and O3. It was all one string, but there should be spaces in between. Yeah. Because one of the common tickets that we get is, I can't install this library, please help with the library. So one of the slides is trying to explain that. Yeah. I know each library is very different, but that's a common thing. You had a question? Yeah, yeah, I know if it's not maintained. It's hard because if you have a dependency on the library which is maintained, but then it stops being maintained. Yeah, sorry, I don't have a. So he uses a library eigen, and it's not being maintained any longer. So the developers stop maintaining, so it'll start to go out of date. And the question was, how do you protect against that?
Or like you have like a similar situation or something.
I haven't personally, so I'm not sure how to protect against that. I guess if it's a big team that is developing, you have a better understanding that it might extend longer than, I don't know, a couple of years. But normally if it's like one developer, it's a higher chance of it's not gonna, but you don't know. Each case is different, yeah. So it's 9:45 now. I think yeah. But if you have any more questions, please feel free to contact me. So thank you.